Okay, so here basically I want to show another example. So last year actually I gave a seminar at the 600 seminar series about pathology imaging, how we can create efficient 3D databases for 3D pathology images. So here I want to show an example for a 2D-based approach, 2D spatial database, parallel database for managing extreme scale spatial data. So as I mentioned the last time in the seminar, basically pathology images is a new flavor of medical images. So traditionally, pathologists use a microscope to view a tissue, to look at, to make actually the final diagnosis to see if there's a certain disease or not. So in general, if you want to have a final diagnosis, you have to use biopsy or tissues. Basically, the pathology lab will make the decisions using a microscope. So basically, pathologists have to use a microscope to read a lot of information from the tissues. So that's too difficult for pathologists to, and also in many cases not efficient because there's too much information from a single image because a single tissue may have millions of nuclei, cells, and a lot of other information. So instead, we can use a computer-based approach. So we can extract all the information from medical images. So we segment the boundaries of cells, blood vessels, and so on, and we extract features as well. So eventually we convert the image information into spatial data. So we have the boundaries, we have a lot of polygons representing the microanatomic objects. So here basically we have nuclei. And also we have all kinds of features about such objects, such as area, parameter, and so on. So basically we can extract hundreds or thousands of features. So eventually, based on such a structured data derived from the images, we can provide all kinds of image analysis, we can do classification, we can combine the data for further analysis, for example, to predict the survival of patients and so on. But there's too much data generated, basically, since one image may contain millions of objects, and each object may have hundreds or thousands of features. So eventually we have tons of data generated from such images. And many of them are spatial-based information because we want to find spatial relationships between such objects. For example, we want to find the shortest distance between blood vessels and cells, and other similar kind of spatial queries as well. So basically, eventually we will provide scalable spatial query processing for large-scale data derived from microscopic pathology images. So basically, we develop a parallel-based database approach at the very beginning. So this is suitable for small-scale data. For example, if you have one small data set, for example, tens or hundreds of images, so the data generated will be around 1 terabytes. So that's very suitable for a parallel database-based approach. So we provide a very comprehensive architecture for data loading, data conversion, data parallelization queries, and so on. So this is the data model, and we have many tables for representing all the information. So in general, we have geometry data, the points, polygons representing microanatomic objects, and we also have features data, patient data, and so on. Okay, so to make the database scalable, so we have a parallel spatial database architecture. So again, we built this prototype on top of DB2. So we have, so for this case, so we have only 2 nodes. So each node has 15 partitions. Node 1 and node 2. Node 1 has 15 partitions, and the second node also have 15 partitions. So we have a master partition. This master partition will handle all the user requests. So whenever you submit a query to the database, the master partition will take your query and will translate the query into multiple parallel jobs across all the partitions. So basically, we have a single master partition, and all other partitions are called slave partitions. Okay, so basically once we have all the data loaded in the database, including the geometries, we can provide all kinds of operations. For example, we can query the data directly, and we can visualize all the boundaries just with a single query. And we can also easily query the features. We can do feature aggregations and so on very quickly just with SQL-based operations. We can quickly generate a histogram of features using SQL. So this is a web-based interface. Basically, this web RESTful-based API will be mapped to an internal SQL query. So all this will be extremely efficient. We can, from 1 terabyte of data, we can generate a histogram with a couple of seconds. And also we can do similarity queries by just looking at the features, image features. So I will, okay, ignore the details of the queries. Basically, we can support all kinds of queries, including spatial queries. So as I mentioned at the very beginning, parallel database data loading is a major bottleneck. And to make the data loading more efficient, we have to use multiple CPU cores. So instead of using a single thread, actually you can use all the CPU cores to load the data in parallel. So that's much more efficient. So the second graph basically shows the loading time drops quickly if we will increase the number of threads for data loading. Okay, so next I want to quickly show how we can set up a parallel database for such a purpose. So for this case, we have two nodes. We call it node 40 and 41. Each node has 16 cores. And we reserve one core for operating system, and then all the other CPU cores will be used for the database. And eventually we have a DB2 with 30 partitions. And so each node will have 15 logical partitions. So to set up DB2 in this environment, one thing we need to do is that we want to share all the binary codes. So these two nodes should have a shared network shared drive. So all the DB2 binary should be stored at the same place. That means we don't need to have the physical copy of the installation. So we only need a single binary across all the nodes. Even you have 100 nodes, you only need a single binary for the DB2 software. And for each node, for each physical node, so here we have two physical nodes. We need to create a DB2 user and to set up DB2. Since so we need to have two kinds of setup. One is for the master node. The master node, since it's different from slave nodes, so you have to have separate setup for master nodes, master partition, and slave partitions. So instead of using the DB2 setup GUI interface, there's one approach using a response file. So you can create a DB2 setup with a GUI interface that will generate a response file, and then you can use the command line to quickly set up for all the partitions. So that's one trick. Basically, we don't need to use a GUI interface for all the setup, and we can just use a script to set up everything very quickly. Okay, so once we have a database set up for each node, so here we have two nodes. For each node, we want to create 15 partitions. So what we do is that we just need to change the configuration file, and we have a list of partitions for each node. So we have an index for each partition. So for example, we have the partition 001 until 14, and the node name. Similar for the other node, we have a list of partitions. So this is like a directory of all the database partitions. Eventually, DB2 will look at this partition directory to do all the parallelization. Okay, so then once you have the partition set up, the next step is to create a table on top of the partitions. So you can customize how the table will be built on the partitions. So for example, you can use all the partitions. So for example, for this database, we create a database. We first actually create a different combination of partitions. So I can have a partition group that includes all the partitions. Or I can have a database partition group that only uses a single partition. And once you have the partition groups created, then you can create a table space on top of the partitions. So for example, I have a table space, something called master, that will use first partition group. That means this table space will combine all the partitions. And once we have the table space, then we can create the table. Okay, let me see. Okay, there are different kind of tables to be created. Okay, so first one is a table that we use all the partitions. So okay, we create a table. So the most part is normal, and then we at the end we have we select a table space. We create this table in this table space. So this table space is defined on top of all the partitions. So once we choose this table space that defines this table will across all the partitions. And then we also need to specify how we should distribute the records. So we specify all the records will be distributed based on a hash function, based on something, a column name called tile name. So this is basically for creating the distributed tables. And also we can create a replica table. As I mentioned, for small tables, we can just replicate it across all the nodes. So we can actually create a table and have it replicate. So we create a table, and actually there's some syntax, and in particular, there's an option called replicate. That means everything for this specific table is automatically synchronized across all the nodes, all the partitions. So that's for replicate tables. And also we can also create a non-partition table. So if you create a table in a table space using a single partition, then that's it. There's no parallelization anymore. Okay, basically you can say we have three flavors for tables. Replica tables using multiple partitions, non-partition tables running on using a single partition, and then replica tables that are copied across all the partitions. Okay, similarly, this is another table for polygons. Again, we partition that across all the partitions through using this specific table space. Here you can see we also have another option called compress. So that means this whole table will be compressed. So since the polygon could be very big, we can compress data to make it much more efficient for the query performance. And then we will create additional keys and indexes, and we have scripts for the data loading and other things. Okay, so this is the performance. So we did different experiments utilizing different number of partitions. So if we use 5 partitions, this is query performance, the time to run a single query. So this single spatial join will take almost 1 hour. I think it's about 50 minutes, 45 minutes or something. And if we increase the number of partitions, with 30 partitions, it will take less than 400 seconds. So you can see there's almost a linear performance increase with parallelization. So again, for parallel database, the big advantage is that we can utilize SQL. So we don't need to write any program codes. So we can just use SQL to create the tables, to define the partitioning, and everything. And then eventually we can just use SQL to perform all the queries. So from user point of view, it's much